The previous two chapters have covered the basics of programming, and that is conditional execution and iteration. In this chapter, we start out on recursion, and basically a recursive function is a function that has the ability to call itself. Now, R does support recursive functions, and the example that we're going to use here, we're going to write a couple recursive functions to compute the factorial function. There is already a factorial function built into R, and here it is, factorial of 5, and you'll notice that this includes error checking. So if I take the factorial, for example, of -1, it'll give me a warning message saying that it computed the factorial of a negative number and that the gamma function can't handle that. The gamma function is undefined at negative values, negative integers, that is. But it will handle, for example, the factorial of 3 through 7, and it will take that vector and compute the factorial of 3, which is 6, factorial of 4, which is 24, etc. Now, this factorial function works fine, but we're going to try writing our own factorial function. So I will go up to the top here, since we're in programming mode. And let's see if there is anything, before I do that, see if there's anything that exists in R, such as fact1, because I want to use that name, as well as fact2, and I'll even write a third factorial, fact3. So those aren't anywhere out there, so those are safe names to use. So we'll start out with fact1, and this will be a function of x, which will be the input argument. And in this particular case, I'm going to use loops to write this factorial function, and start out by setting I to 1, and then do a for loop for j from 2 to x. And what do we want to do inside this for loop? We want to take I and multiply times j and place that back into I. So for example, if you send it an x, for example, of 3 as an argument here, what will happen is I will initially get set to 1, then j will loop from 2 to 3, which means it's going to go through this for loop twice. There's only one statement in the for loop, so we don't need any curly braces. And the first thing it's going to do is multiply I, which starts out as 1, times 2, and now I will get set to 2 on the first pass through the loop. Then on the second pass through the loop, j will take on the value 3. So now what you will have is 2 for I multiplied by 3 for j. 2 times 3 is 6. And it will end that for loop. So what we want to do at this point is return the value of I. Let's run this factorial function. You can see down here it executes without any difficulty. So now let's call it with an argument of 5. And when you do that, you can see you get 120. Now, there's no error checking in here. If I put in, for example, a vector, or if I put in a character string, it would have problems. But right there, it didn't have any problems. Now, let's try a more compact factorial function. This time, I'm going to say fact2, so this is second factorial function, is a function of x. And this time, I'm going to use the product function and basically just say I want it to be the product from 1 to x. We don't need any curly braces or anything else. It's just that right there is fact2. So I will highlight it and run it. You can see down below it executed without any difficulty. And then if I try fact2 of 5, that will also return 120. So far we've managed to write 2 factorial functions, but we haven't used recursion yet. So this is a third factorial function. I will call it fact3. And in this particular case, there is something called a base case. So we want this recursion to end, and what we're going to say is if x is equal to 1, then we want to return a 1. Otherwise, what we want to return is x times fact of x minus 1. And that right there is a recursive function because it is calling itself, fact 3. So the name of it is factorial 3. It takes a integer, positive integer, as an argument. If that integer happens to be 1, it'll just return a 1. Otherwise, here's what happens. Let's think through this when you pass it, for example, 5. When you pass it a 5, this particular condition will not be satisfied, so it will go to the else clause, and it will multiply 5 times 4 factorial. And when this function is called with a 4 to calculate 4 factorial, it will go in here and it will say, is x equal to 1? And it is not, it is 4. So it'll come back here and say that is 4 times 3 factorial. And when it's called with 3, the if condition fails, so it will call 3 times 2 factorial. And then finally, when the 2 factorial is sent in here as an argument 2, it'll say if x is equal to 1, it's not met, so it'll return 2 times 1 factorial. When it calls 1 factorial, you notice that it keeps getting deeper and deeper here in terms of multiple calls to factorial. When 1 is called, it will return a 1. And then back up the chain, it will be doing one return after another, and finally it will come back and it will return x factorial. Let me highlight this whole thing, and let's push run, and it took it down below here. And now let's try down below in the lower window. Let's try fact 3 of 5. And when you run it, you'll get 120. So notice the fact 1, which involved a for loop, gave us 120. Fact 2, which involved using the prod function, also gave us 120. And fact 3, which used recursion, also gave us 120. So you can see all 3 of them there. Probably the least effective in terms of computer time is using the factorial function. But as you read this chapter in the book, you'll see that some difficult problems, such as the Tower of Hanoi problem being solved using recursion, it is very, very effective. So it is a great tool illustrated here on this easy problem of a factorial. If you read on in the chapter, you'll find more challenging problems.